Hi everyone. So we are still in chapter 5 and I'm going to do a short review just to keep you in the loop that we are studying the sun. And in studying the sun, we're studying just about every other star because the sun is a typical star. So in studying the sun, we look at it from a perspective of the core to the atmosphere, and we look at what we can know from our observations of that core to the atmosphere. And what we can know about the temperature of the sun, we can know about the composition of the sun, what elements it's made out of, and also we can know about the speed of some of the forces on the sun and around the sun. So let's do a quick review of that. According to the law of equilibrium, like I had mentioned in another video, the sun does not explode from the nuclear fusion in its core because the huge mass of the sun exerts so much gravity. So there's gravity pulling in and explosive fusion pressing out. And that fusion is due to the insane temperature at the core of the sun that is fusing together hydrogen atoms to produce helium atoms. And in fusing together 4 atoms into 1 atom, you're dramatically lowering the energy level of the new helium atom. 4 atoms into 1 means that you will release energy in the form of photons. So these are the photons right here, and this is the photon release as gamma light rays when you go from 4 hydrogens to 1 helium. Now the sun produces an enormous amount of helium, and it also produces many other elements as well. And helium is just one of them. Whenever the hydrogen is moving and fusing into other elements, it will produce lower energy elements that are more structured, lower energy, and it will produce a release of photons. Now you know from what we said that those photons can really energize electrons. So electrons around the ground state in an atom can get energized by photons and go up to an excited state. And that excited state lasts for only about a moment because then the system wants to achieve and balance out an equilibrium again. The law of equilibrium states that every system in the universe seeks equilibrium. So the electron is most stable at its ground state, its rest state, and if it is energized by a photon, it's going to then turn around and emit that photon and emit that light, and the electron will go back down to its ground state. When that photon is emitted, that is a photon, that is a packet of energy, a packet of light. You could say that a photon is a packet or a parcel that carries waves of energy. We talked about the fact that energy is a wave and it is a particle, and it has characteristics of waves and it has characteristics of particles. And this is not easy to understand. And you should know that in the ground state, electrons gain photons and go to an excited state. Then they lose photons and emit that light and that energy. We talked about that emission and those photons as forming an electromagnetic spectrum, and that these waves of light that are produced by the core of the sun have a length, a wavelength, and that the higher the energy of the wave, the shorter the wavelength. An example is gamma rays. Gamma rays are deadly to you and I. But on the other hand, radio waves are something that goes in one ear and literally out the other. Not deadly at all. So this is a very high energy wave that can kill us, and this is a very low energy wave that can entertain us. That fusion at the core of the sun makes all the energy, basically makes all the energy and all the wavelengths that hit the Earth. They radiate from the core of the sun through the radiative region of the sun and out to the convective region of the sun. So these photons move at the speed of light through the radiative region, and that takes an enormously long time to do because of the intense gravity of the sun. So gamma rays, those rays that can kill you because they have so much energy, those rays take 171,000 years after they're created in the core of the sun to get to the surface of the sun. Crazy. That's the gravity that we're talking about. That mass means that that photon in the core hits so much matter and gets absorbed so many times that it gets slowed down, and it takes 171,000 years to get to the surface. And that's a gamma ray. So you can imagine what radio waves take. Hundreds and hundreds of thousands of years. When we talk about the convective regions of the sun, that is a relatively lower temperature. And those convective regions move more slowly, much like lava lamps move more slowly, and lava lamps are convective energy as well. If you want to look at it another way, this core moves through the radiative zone to the convective zone. Remember, you've seen a lot of circles in the convective zone like lava lamps. All right, they move out to the sun's surface, which is called the photosphere. The photosphere is the sun's surface. That's what we see. And if you're looking at the temperature of the core to the photosphere, you see that dramatic drop. That dramatic drop is measured in millions of kelvins. When we boil water, we're talking about hundreds of kelvins. And when this is moving the sun, millions of kelvins, but you see that temperature drop there from the core out to the photosphere. How do we know about these temperatures? Well, we know about these temperatures from spectrographs. We're going to talk a lot more about that because spectrographs not only tell us about temperature, but they tell us about the composition of the sun and of its emissions. And they also tell us about the movement of plasma and gases on the sun, and they also tell us about the movement of plasma and gases on other stars. But let's start with the temperature and the spectrograph. An example of a spectrograph is this device loaded onto the eyepiece of a microscope. And it's in my favorite place, Mauna Kea volcanoes and the telescopes in Hawaii. So when you see a device put onto an eyepiece of a telescope, you'll know that that is a spectrograph. And that is basically taking in the light, bouncing it around, and putting it to a detector. We're going to talk a lot more about that, but that's what you're seeing right here. This is bouncing around on a set of mirrors and on diffraction gradients to a detector that's down here. That detector is putting out an analysis of wavelengths that hit it. And you already know about some of this because we talked about black body radiation. We talked about the Earth is a black body that will accept all radiation coming at it at all different levels, and it will emit based on its own temperature. So we said that an asphalt highway approximated a black body because it takes in all of the radiation that hits it, absorbs all that radiation, and then emits it off continuously as infrared radiation. And so black body radiation will emit all of the intensity of the radiation that hits it, but it might emit it at a lower wavelength. In this case, and you've seen these black body curves before, we can say that our study of the sun is at a certain temperature because of the black body curve that we know from the spectrograph. And what we know is that the hotter an object is, and this is Wien's law, the hotter an object is, the shorter the maximum wavelength. So the sun at 7,000 Kelvin has a maximum wavelength right around 450 nanometers in the visual field. And a star that is cooler than the sun will not only have a longer wavelength, more toward green in the visual field, more toward 500 nanometers, but it will have lower total emissions. So the area under the black body curve will be much less at 6,000 Kelvin. And if you had a star, for instance, new stars are quite cool until they get going. And so new stars would show a wavelength that might be in the red zone, a little longer, and a lower total emissions for 5,000 Kelvin. This is a continuous emission spectrum. We're going to be talking more about that soon. So we can know a little bit about the sun's temperature from spectrographs, but we can go and we can talk about that even more. When we point the spectrograph at the sun, we are taking the spectrographic data from the photosphere. And when we point the spectrograph at sunspots and then add a mask to mask off the rest of the photosphere, then we can really concentrate on the spectroscopy from the sunspot, and we can see that these black areas actually have a lower temperature. They're more like the very cool star. But that makes sense because these are black areas, and black areas are not emitting a lot of radiation. Otherwise, they wouldn't be black. They'd be green, or they'd be red, or they'd be blue, or they'd be yellow. But these are black. They're not emitting a lot of radiation, so they are cooler. So we can find out that from the spectrograph and a mask. The best mask of all is a solstice, and this is why astronomers love eclipses. It's like a beautiful mask that is perfectly designed for the sun. When solar eclipses happen, they will cover the sun's photosphere. That leaves the sun's atmosphere exposed. If you point the spectrograph at the sun, it will record the wavelengths coming in just from the atmosphere. That atmosphere is in two layers. The atmosphere has a pinkish layer and the atmosphere has a whitish layer. When you are seeing the pink, that is called the chromosphere. That is an annular eclipse that you're seeing there. That's why we talked a bit more about annular eclipses in the assignment that I gave to you. That is an annular eclipse here. This is not the corona. Right? This is not the corona. It looks a little bit like the corona, but you'll see the corona in just a second. When you take a spectroscopy clip from this particular solstice, you will get the spectrogram from the atmosphere of the sun, which includes the chromosphere and the corona, which you can't see here because the chromosphere completely obliterates the very faint corona, but it's there. So what you can say is that I can now take the temperature of the atmosphere minus the photosphere because the photosphere is behind the mask. You get a lot of temperature information from the spectrograph. And if you had a perfect total eclipse where you just saw the corona, you see the difference here with the corona. It's very faint. It can actually go out a quarter of the way to Earth, a quarter of an astronomical unit in that very, very faint gas. This is a total eclipse. This is not an annular eclipse. When you point the spectrograph at this to look at temperature, you are getting just the temperature of the corona. So when you subtract out all of these standards that you get, you can really get it at the temperature of the photosphere, of the chromosphere, and of the corona. We'll talk more in just a second.